Now let's get into buffer overflow. That is the second issue we are having. The VM has been restarted. The debugger has been reattached. Everything is back to normal and I have restarted the not my fault. Now we are going to press the buffer overflow as you can see here. Then I'm going to press the crash button. I pressed a couple of times. There is no crash. Not sure what is happening. Probably it is corrupting some memory, but it is not crashing. I'm trying again. There is no crash. All looking good. One of the thing is that there is no crash on buffer overflow. We'll examine it later probably. Probably it is corrupting some buffer, but it's not crashing. So someone else needs to be accessed to get that crash probably. We don't know how it is implemented. Right now we are not getting any crash. Probably when you try this, you may get a crash. As I was mentioning, I have no clue about how this is implemented. Just like you, I am doing it for the first time. It is not crashing. Let's move on to the next issue, which is code overwrite. We will see what to be done with buffer overflow probably later. Now I have selected code overwrite. Now I'm going to press the crash again. Luckily this time we are getting the crash correctly. It has crashed to the debugger. As usual, I'm going to press bang analyze -v. Let's go with the normal bang analyze -v practice. For all the crashes, we will be going with bang analyze -v. So irrespective of what is the output. So it is giving us the very correct information. Attempt to write to read-only memory. It is very accurate for our situation. Assuming the not my fault is telling us the correct problem. It is matching and it is pointing to the not my fault binary. That is the best thing. Pretty much we are done with the analysis. We are getting the correct driver, everything. Not my fault is on the stack. And that's what is being blamed by the bang analyze -v. For this kind of straightforward issues, all we need is bang analyze -v. Now, let's do a little bit more. Let's have a look at the addresses which are trying to access. We have a couple of more information in the bug check parameters. Let's see what are those parameters means and so on and so forth. So in this case, this is the virtual address which it is trying to write to. Virtual address for the attempted write. And this is the PTE content. Let's verify this two information. And this two information is reserved. We will verify the first two information and what that means. As usual, I'm going with the dot trap to see the actual registers. We have the dot trap here. And you can just click on that dot trap. In the dot trap output, we can see the address we are trying to write to. It is 816B C6E0 and that is the byte PTR EAX. This is the address we are trying to write to, 24H. We need to see why we are getting a problem when we are trying to write to this particular address. That's what we're gonna look at. OK command, just to see the stack. The stack is correctly pointing to the problem. R is also exactly same information we saw. That is the address which we are interested in. And that is the exact same address which is being pointed by the bang analyze -v or the bug check code. What I'm going to do is I'm going to do a DC on that address. Let's see what we're going to get. When we did a DC, we are getting valid address. So it's a valid address. It is not an invalid address. It does have pages associated with it. So it is a valid page in terms of backing up with either RAM or page file. But still we are getting problem. Next command we're going to type is bang PTE on that particular address to understand why we are getting problem. Bang PTE that address. We have seen this command before, bang PTE command. Let's have a quick look here. Now this is the flags of this particular page. This is the information we are interested here, this particular bits. We'll understand what these bits are from the debugger documentation pretty quick. In this case, this R right here is a problem. This R means that this page is read-only. If you look here, this part of the page table directory, it is a write. So it has write. permissions, but in this page it has only read permissions. As long as this is a read only, we cannot write into that particular page. We will see that. One more information which is there in the bug check code is the PT content. So this is the PT contents. Let's copy that into a scratchpad just to see if the information is matching with the output of bang PT command. It is indeed matching with the content of the bang PT command. That is in fact the physical address and the flags of the particular PFN. As you can see here, first 4 digit is the PFN and then the flags. The flags are given at the bottom. Don't worry much about it. All we need to understand is the flags. Flags are the entity which gives permission, read or write in this particular case, and different qualities for that page. Let's look at the documentation real quick. This is the documentation of the bang PT command. If you want to have a look, you can have a look. And this is the relevant session which explain what are the meaning of each flag. And in our case, we are interested in the read write flag, which is 02 in the end. This is the flag we are interested in, the read write flag. In our case, it is a read only, and to write into the page, write into that particular piece of memory, you need to have write access. There are other interesting flags right here. One of the flag worth mentioning, valid. Valid or not means that this page is present in the memory or not. If a page is valid, there will not be any page fault exception by the CPU. If the page is invalid or the valid bit is 0 in the page table entry, it means that the physical page is in the page file and a page fault needs to happen to take that from the page file and put it into the memory. That is the valid bit. Another flag worth mentioning is dirty. Dirty means that the content in the memory and the content in the page file is different, which means someone has changed the page inside the memory. That is the meaning of dirty. There is a whole presentation from me regarding this particular flag, UNK, user mod or kernel mod. It's a pretty big topic and one of the backbones of security in operating system like Windows and Linux, this particular bit right here, UNK. I'm not going to the details of it right here, but a lot of these flags are very important and interesting from an internal standpoint. That is the output of bang PT command, and that's how you interpret bang PT command. What it does, as I was mentioning before, it converts virtual address to physical address, and it'll show you what are the flags or what are the properties of that particular page. And this is how you interpret the flag. This is true for x86 and x64, but slightly different for some other platforms. So feel free to look at the documentation. Now to show you how a writable page looks, I'm just going to take a random address from EBX. Looks like a valid address to me. I'm going to do a bang PT on that address just to show you how a writable page looks from the bang PT perspective. Bang PT, that particular address, it's a random address. I'm going to check if it is writable. That page is indeed writable. What I'm going to do is I'm going to do a DC on it. This particular bit right here is W, which means that it is writable. This particular address is writable, but this particular address which we have the issue on is read only, this particular bit. There is a executable bit as well, so which means that this page is executable as well. This second bit is executable, E. This is valid, we discussed. This is an executable bit. So it's very common to have executable bits or executable pages are read only. They are normally pointing to binary. Feel free to do an ln and see if it is between some binary or U on that address. You may get some valid addresses. So you may get some valid instructions on that particular address. This is not showing any value, but it's still a valid address. The value inside that address is just 0. That doesn't mean that the address is invalid or anything. So it's a valid address which is writable. So we tried the memory corruption, it didn't crash the system. And then we tried to go with the next issue, which was writing to a read-only page, and we got the crash. We looked at the bang_alias-v, it was very conclusive, it was pointing to the correct driver. Remember, our aim is to point to the correct binary. So as long as it is pointing to the correct binary, we are good to go. As an add-on, we looked into the bang_pt command. We looked at what is a readable and writable page, read-only page, and we saw the difference in the bits inside the page table flags, or the flags associated with the page table entry using the bang_pt command.